Engineers risked their lives to erect the world's tallest bridge pillars, but now they face the challenge of connecting them. In France, during the construction of the world's tallest Milau Viaduct bridge, engineers found themselves in a serious dilemma. They needed to place prefabricated road sections between two pillars, each weighing the equivalent of 25 locomotives, and there were a total of 8 sections. There wasn't a crane in the world capable of lifting 5,000 tons to a height of 800 feet. If they tried to lift the road sections with a crane, the tall pillars could easily collapse inward. The construction of the Milau Viaduct was delayed, incurring a fine of $30,000 for each passing day. The Milau Viaduct in France, completed in 2004 at a cost of €394 million, stands at a height of 1,125 feet, making it an engineering marvel. It towers 45 feet above the Eiffel Tower and often appears to float among the clouds. The engineering company behind this ambitious project faced several challenges. Landslides and stormy winds of up to 130 km per hour were complicating their efforts. Building such a high 4-lane highway had never been attempted before, pushing the limits of engineering. Furthermore, it had become a necessity for the French government, which had been struggling with traffic congestion, particularly during the holiday season, as tourists traveling from France to Spain caused gridlocks in various cities. To facilitate this traffic, the government planned to create a motorway from Paris to Spain, which could not bypass the Milau region due to a 1,500-foot high mountain and the Tarn River. The only solution was to build a bridge nearly as tall as the mountains. However, during the 1980s, when the plan was proposed, the tallest bridge in the world was California's Golden Gate Bridge, which was only 250 feet high. Many experts deemed a bridge over Milau impossible, fearing it could lead to a catastrophic failure. For years, the dream of building the bridge remained just that, a dream. But as traffic jams worsened, the French government had no choice but to move forward. The engineering team faced 3 major challenges: erecting the tallest bridge pillars on sloped terrain, placing a 36,000-ton 4-lane highway on top, and constructing steel pylons. These pylons were twice the weight of an Airbus A380, and all tasks had to be completed hundreds of feet above the ground. The project hired renowned architect Lord Norman Foster, known for his innovative designs. However, his reputation suffered after the failure of the Millennium Footbridge in London due to a hidden design flaw that caused it to sway dangerously. As a result, the engineering team was under immense pressure. After 2 years, Foster presented a stunning design involving 7 pillars, with one pillar being the tallest and the others on a slope. However, constructing this unique design was a monumental task. The team was given a strict 4-year deadline, with fines accruing after that. The construction began in October 2001 but soon faced geological challenges, including the discovery of a fractured limestone area that posed a risk of landslides. Despite warnings, foundation work proceeded, leading to an unexpected landslide that covered the first pillar's foundation, fortunately without causing damage. To create the 7 massive pillars, 200,000 tons of reinforced concrete were required, necessitating a factory on site. The project used an enormous amount of steel bars. As the project progressed, concerns arose regarding the uniformity of the pillars, which had to be perfectly aligned. The construction team utilized GPS technology to ensure precise placement of the pillars, and by November 2003, the pillars reached their final heights. The next challenge was to place the 36,000-ton road section at such heights. To ensure safety, the road was constructed in sections, with a plan to weld them together and slide them into place. However, the unique conditions of the Milau Viaduct required an innovative approach involving a hydraulic ramp system to lift and push the road sections into position without putting excessive strain on the pillars. On February 26, 2003, the construction team conducted a crucial test of their system, successfully aligning and connecting the road sections with remarkable accuracy. Following this, steel pylons weighing 700 tons each were erected for additional support.